Let's continue working with lesson 3.5 and graphing multiplicities. Now in the last video we defined odd and even multiplicities and kind of what they'll look like. And we graphed just a couple of functions up on the top with multiplicities of 1 and 2. Down below on the left hand side, f of x equals x minus 1 cubed times x plus 2. To find our zeros, let's first take a look at how many we should have. We've got a degree or an exponent of 3 in that first parenthesis, and then the second parenthesis, technically that would have an exponent of 1. That means this is going to have a degree of 4. And looking out in front, I see no positive or negative integers to worry about, which means it would default to positive. Our a value is going to be greater than 0. That means our parentheses or our arrows would open up. So now let's look specifically at where it'll cross the x-axis by setting the entire equation equal to 0. We're going to get the same x-intercepts that we did up above. X minus 1 equals 0, x would equal 1. Due to that 3 though, that's a multiplicity of 3. And like we said in the definition, that's going to kind of slant through that 0, which will look really weird. So it'll kind of come up, an angle to the right, and kind of keep going. That's what it would mean to kind of slant through that 0 on the graph. All right, the other 0 is going to be negative 2. We'll just subtract 2 to move it over. And that has a multiplicity of 1, which just means it's going to go right through that location. So we'll put negative 2 on the left, positive 1 on the right. Now remember, we said before it was a degree of 4, that's even, and a is positive. That means on the left-hand side and the right-hand side, the arrows would point up. On the left, it'll come down through negative 2 like a normal looking 0, although I missed that just by a little bit. Let's try that again. So it should come down through negative 2. Well, it's closer. All right, we're just going to go with it. And as it comes back up and makes that turning point, it's going to get closer to that 0 on the right and then kind of slant its way through and then go up towards positive infinity. So notice it kind of just angles its way through that positive 1, and that's a degree with that's a degree of 4 with a multiplicity of 3. Let's try that last one over here on the right. This is going to be the most unique looking one out of all of them. We have a degree of 4 for that first parenthesis, and technically a degree of 1 for that second parenthesis, making the entire polynomial a degree of 5, which is odd, and then a would be greater than 0 again. That means on the left it'll fall, so the arrow will be down here when we're done, and on the right it should rise, so it should be somewhere over here at the top. If we set a parentheses equal to 0, again, no surprises for where our zeros are. We have x equals 1 and x equals negative 2. But this 1 over here on the left has that multiplicity of 4. And that means it kind of flattens out at that 0 and is a turning point. The negative 2 is just a multiplicity of 1, so it's just going to go right through it. So here's what this graph is going to look like. Let's see if we can make this shape happen. It's going to come up through that negative 2 on the left and have a turning point and make its way back down. As it approaches 1 on the right, it's going to kind of flatten out as it intersects that 1 and stays flat until it goes back up again. All right, let's try to see what that's going to look like. It's going to go up through that negative 2, and as it comes back down, what ends up happening is it kind of flattens out. Let's see if I can make that happen. Oh, I was pretty close, wasn't I? And goes back up like so. So it flattens out when it intersects that 1 and then comes back up. I know, kind of strange looking. We won't have a lot of multiplicities of 4 on our graphs, but that's what it would look like. Let's take a break from graphing for a minute and go back to using something that we talked about in our previous lesson that we actually kind of liked. If we're looking at a graph and trying to find zeros, we're going to go back to using synthetic division. And that will verify algebraically that a number on the graph is an x-intercept. It says what are the real and complex zeros of the polynomial function shown in the graph. Here's our polynomial, And if we look at the picture of the graph, obviously it looks like it's a cubic function because it falls on the left and rises on the right. And that would be the sketch for an odd function. And by looking just at the picture itself, it looks like it crosses the x-axis at 2. The 0 that we can determine then is x equals 2. To verify it, we'll do synthetic division. I don't know what I was going to write there, so we're just going to get rid of that. All right. If we plug in 2 to the penalty box, let's make sure all of our coefficients are present, or our terms are present. X squared, x cubed, negative 3x, negative 6, all of our terms are present. Our coefficients are 1, 1, negative 3, and negative 6. We'll draw our blue line in here. Let's verify that we have a 0 for this polynomial. I'm going to drop the 1 down, multiply with the penalty box. 1 times 2 is 2. Add the column, 1 plus 2 is 3. Multiply by the penalty box, 3 times 2 is 6. Negative 3 plus 6 goes back to 3 again. 3 times 2 is 6. And we get an output of 0. That would be our remainder, which verifies that x equals 2 is a 0 of the function. Now that's just the first part. We now have to look for the other zeros for this polynomial. That means we're going to take our quotient and do 1x squared plus 3x plus 3. We need to solve this. And this is quadratic. This brings us back to topic 2, working with quadratic functions. We can solve by either factoring or quadratic formula. Now, take a look at the picture. Can you see where it crosses the x-axis at any other location besides 2? I don't see it either. That's going to indicate that we don't have any real solutions left to determine. And if we look at setting x squared plus 3x plus 3 equal to 0, it does not factor. We can't come up with two numbers that multiply to get 3 on the right, but then add to get 3 in the middle, which means we need to do quadratic formula. To verify that there aren't any other real zeros, meaning we would have complex zeros, we'll do x equals negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. Simplifying that, we get negative 3 plus or minus, and we end up with 9 minus 12 all over 2. That would give us negative 3 plus or minus the square root of negative 3 all over 2. Now we know that indicates no real solution, but it does say to state the complex solutions. That means we have to simplify. We'll take the negative 3 plus or minus, we'll factor out our negative by putting I out in front and divide it by 2. And you know what Pearson's going to have us do. With a complex number, we need to split this into both parts. So we'll do negative, I don't know why I did 2 arrows there. I don't know, you guys. It's been a crazy day. We'll do plus or minus, and I'm just going to rewrite that as well. We don't even need any arrows at this point. We'll do negative 3 halves plus or minus I radical 3 over 2. Those would be our complex solutions, and we verified that 2 was a real solution. Let's do a little application with interpreting zeros. Acme Innovations makes and sells lamps. Their profit in hundreds of dollars earned is a function of the number of lamps sold. They have to sell lamps to make money. From historical data, they show their company's profit is modeled by the function shown. What do the zeros of the function tell you about the number of lamps that Acme Innovations should produce? Taking a look at that picture, you can see it crosses the x-axis at 3 different locations. On the left, over here in the middle, and on the right. So our x-intercepts are at negative 2, 3, and 10. But lamps are sold in the thousands. That actually means you have an x-intercept at negative 2,000 lamps, positive 3,000 lamps, or 10,000 lamps. Thinking about what gives this function meaning, we can't have x number of lamps. This cubic function then has an irrelevant 0. That 0 at -2 doesn't give us any meaning. And if we take a look at where we should start kind of looking at our profit as a function of our input, we'd have to start at 0, 0, right here. We don't want to go below the x-axis, so that bottom part over here on the right doesn't help us out either. If we want to make money or make a profit, we would want to be in that top bubble somewhere. As long as Acme sells anywhere from 3,000 to 10,000 lamps, the output is above the x-axis, it's positive, and they would make a profit. Let's go ahead and omit this example. Our final example in 3.5 will be solving inequalities. We'll look at finding zeros and we'll look at end behavior to solve inequalities using higher ordered polynomials. When you solve inequalities, the first thing you want to do is figure out the degree and then the end behavior, just like we did before. And it'll follow the same rules for inequalities as it did for equations. Then we're going to find our zeros, and this might be easy or challenging depending on the type of function that you have. Finally, we'll determine the interval solution for our inequality. Okay, let's take a look at the example on the right. What are the solutions of x cubed minus 16x is less than 0? Let's start with this polynomial. What is its degree? If you said 3, you'd be correct. That is the biggest exponent. 3 is an odd number, and the number on front technically is 1, and that's greater than 0. That means the end behavior on the left side, it falls, and on the right side, it rises. That's one thing that we need to know. Then we'll take a look at finding zeros. To find the zeros, we have to set it just equal to 0. Don't worry about the less than symbol. X cubed minus, X cubed minus 16x equals 0. Trying to look at how to solve, we could factor out an x, and we'd have x squared minus 16 left over. And x squared minus 16 is a difference of perfect squares. That would be x plus 4 and x minus 4. Notice we have 3 different x's. That means we'll have 3 unique zeros. That first outside x equals plain 0. X plus 4 would cross at -4, and x minus 4 would cross at 4. Let's create a really quick sketch for this graph. I'm just going to make an xy axis and count 5 to the right and 5 to the left. Recognizing our zeros are at 0, -4, and +4, I'm going to mark their boundaries with open circles because my inequality is just a less than. I'll put an open circle at 0, an open circle at +4, and at -4. Ultimately, we're looking for when the output of this function is less than 0. So if we sketch our graph using our left side, right side behavior, the graph should fall on the left. That means it's going to go up through that 0, come back down at some point, and then go back up to positive infinity. It falls on the left and rises on the right. If you can get an idea of what your sketch looks like, we're almost done. We want to know when our values are less than 0. So that means our values are going to be negative or below the x-axis. My answer is going to be over here on that left-hand side and between these two zeros on the right-hand side. To write that out as an interval or an inequality, an interval would mean we're going to go from -infinity. Wow, I really just did that. Okay, -infinity to -4. As an inequality, it would just be x is less than -4. The bubble in the middle goes from 0 to 4, and because they're open circles, we'll put parentheses on both of them. Or we would say 0 is less than x, which is less than 4. So this would be your interval notation or just as inequalities. And Pearson will ask for one or the other. Whew, all right, that is lesson 3.5. Please make sure these notes are completed and ready for class the next time I see you.